Hi guys, this is GKCS. We're going to be talking about Pishty and his birthday today. So Pishty on his birthday got lots of cakes, n cakes, and each cake is represented by a 4x4 matrix. So all the cells in this matrix represent a candle, right? Each cell represents a candle, and if that cell is set to 1, it means that the candle is burning. If it's set to 0, then the candle is off, it's not burning. Now our job is to play games and tell us that who's winning in a particular game. So here's how it goes. You have n cakes. You'll be given a range from left to right and you'll choose all those cakes. First you'll set them all aside in one place. Now you can make moves on in this game. So you can choose a rectangle within any given cake. So firstly, you choose a cake amongst the range that you have. You choose a rectangle, let's say this rectangle, and you set all the candles in that to 0. So this is what's going to happen. If you make this move, then these candles are set to 0. There is one constraint on the rectangle that you choose. All the candles in that rectangle should be burning. So if you choose this rectangle, that would be illegal. So you can't choose this rectangle. You could, however, choose this rectangle. All candles in this are burning. So let's just set this to 0. That's 0 here, 0 here, and 0 here. Now you see that there will come a point when this cake will have no more candles burning. So if you choose this and set it to 0, choose this and set it to 0, now you see that this entire cake has no candles burning. So this cake can't be chosen at all. There will also come a point when all the cakes have all their candles switched off. At that point, the person whose turn it is to play will lose. So you have no possibilities to play, therefore you lose the game. So that's the result. And we have to say, for this given range of left to right, who is winning. Right, so this is the result that we need to give. Who is winning? Whether is it Pishty or his friend called Lotzi? Yeah. I don't know where they got the names, but we need to bear this. Left and right. There's another kind of operation that can happen. They could pick up any cake at index I and set the candles randomly. So they can set it to 0s or 1s or whatever they want. So let's say this is the index I and they set it to all 0s except the last index is 1. So then this cake will be set to 1. This cell will be set to 1, and now depending on your left and right, your answers might change. So two kinds of operations: updates, point updates, and queries, range queries. These are the two kinds of operations you have. A prerequisite for this is to know about Grundy numbers and the Sprague Grundy Theorem. So if you don't know about them, you can check them out in the description below, but that is a prerequisite. So without that, we won't be able to solve this problem. Right, now let's try and understand how we are going to represent each state in this game. Pick up one cake. You'll get different states for that. So let's pick up the simplest one with all the candles blown up. Alright, all of them are set to 0. So Grundy of this state is equal to 0. That's our base case. Why? Because you can't make any moves on this cake. So you have nothing to do. Grundy of the null set is equal to 0, and therefore we have Grundy of this state is equal to 0. What if you have one candle burning? Well, the only position that you can go to is the board having all of its candles set to 0. So the only position you can go to is 0 max of that, and this is the standard formula to find Grundy number of a given state. Max of 0 is equal to 1 because that is the smallest number which does not exist in the set. 0 after that 1. So Grundy of this is equal to 1. Alright, simple enough. What if we have another candle burning right here you could go to two states. You could just take this out, take the entire rectangle out, this rectangle. That would give you 0. So Grundy of 0, that would be 0 is in your set. You could take out this single cell rectangle, that would give you Grundy of 1. And you could take out this rectangle, also single cell, that would also give you Grundy of 1. So max of this is equal to 2. Right, so Grundy of this is equal to 2. Unfortunately, we can't go on doing this for all possible values manually, because there are 2 raised to the power 16 possibilities in this matrix. Every cell can be either on or off, so that's 2 possibilities. And there are 16 cells in this matrix, so that is 2 raised to the power 16. That's a lot. You can't do that manually. So we need to find a way to automate this process and find out for every possible matrix what is the Grundy number of that. So let's understand how we're going to do that. Alright, so we can finally take the toughest case, which is all candles in this matrix are burning. So what we need from here is the Grundy number. And you know how to calculate Grundy numbers now. It's max of all possible states from this state. So what is that? One of the possible states is to take this entire rectangle, blow out all candles, and get a rectangle having all candles set to 0. Another state is to keep one column alive, let's say the first column. This column is alive, and the rest is set to 0. What do you see here in these two states? This state can actually be converted to this. So when you try to find out the Grundy value of this state recursively, you will be again computing this state, the state having all candles set to 0. So we are seeing some sort of recursion here, and it would benefit us if we could use some memorization. So using some memory, if we store the value of this state, we won't need to compute it again and again and again. Alright, these two things, when they come together, usually they mean one. Dynamic programming is what you need to do. And there is a way to go bottom up on this, but I personally would prefer a top-down approach, because the top-down approach is simpler in this case. Alright, so there are 2 ways in which dynamic programming can be implemented. One is the bottom-up approach, in which you take really small problems and you go on building them to get to the bigger problems like this one. And the second approach, which is top-down, which we'll be taking, is to take a really big problem, recursively try to evaluate it. Whenever required, you evaluate. If not required, if you have already memorized it earlier, if you have it stored in the array, then don't evaluate it again. So that's the approach that we are going to be taking. Let's see how. Imagine that this entire number, this entire matrix is defined by a single number. This matrix is also defined by a single number, and so is this one. I'm not talking about the Grundy numbers, I'm talking about defining the matrix as a single number. Alright, so how can you do that? You have 16 cells, each one can be 0 or 1, so 2 types of 16 cells, 2 raised to the power 16. Which means each matrix can be represented by 16 bits. Alright, each bit can be 0 or 1, which in turn means that a single int, an integer, can represent the entire matrix if you set the zeros and the ones in the right places. So this matrix here can be represented as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This is what this matrix can be represented as an integer. And this value is somewhere around 65k. Alright, what about this one? we can represent it as 1, 2, 3, 4, 4 ones, and then the remaining zeros. That would be some number again in binary. This is all zeros. So you don't set any bit, you keep it all zeros, and in binary this is equal to 0. So you have 65,000 possible combinations, each combination being represented by a single int. And that is how you represent all possible states for this game. That's great actually. You can represent all 65,000 states by a single int. So each state will also have a Grundy number now. Whenever you want the Grundy number of a given state, you can recursively find out what the value is using some memorization to speed things up. So you will have an array of G Grundy for any given state over here. You go at that particular index, let's say index 0, and from here you recursively find out what this value should be. So initially all of them are set to -1, and as and when you compute them, you go to that particular index, recursively find out what the solution is, and then set it to the proper value. So this is of course the base case. Grundy of 1 could go to Grundy of 0 only. So you come here, you check, see that the value is 0. Max of 0 is what you'll get, and that will be equal to 1. Grundy of 2 can only give you max of G of 0 and G of 1. So G of 0 is 0, G of 1 is 1, max of that is equal to 2. And that's how you'll be calculating the numbers. So of course here I'm trying to do some sort of bottom-up approach, but you can keep it simple. You can just come to this very number, which is about 65k, and then recursively find out what are the Grundy numbers. So we now know how to calculate the Grundy numbers. Let's understand which Grundy numbers are relevant to one position. Okay. So I'm going to keep things very simple. I'm going to take every possible rectangle in this matrix and check. What I'm going to do is I'm going to check if that rectangle has all of its candles set to 1. That would be that they're burning. If they're set to 1, then I blow out all the candles and find the Grundy number of the new position. Alright, and using these new positions, I can then find out the Grundy number of the original position. That's exactly what I'm going to do. In fact, let me just write down the code. We have Grundy of a given position defined as for I equal to 0 to 4, in fact for I equal to 0 to 3, for j equal to 0 to 3, and this is incorrect. This is somewhere that people make a lot of mistakes. J is not equal to 0, j is equal to I. What do I and j represent? Well, I represents the starting row and j represents the ending row of the rectangle that you're choosing within this matrix. Okay. Now let's go for the starting and ending columns. So let's call it K. Starting column goes from 0 to 3. Ending column L goes from K to 3. Now you can see that this represents every possible rectangle in this matrix. So for example, if I, J, K and L all are 0, then you have this cell over here. This cell over here. 0, 0, starting ending row, 0, 0, starting ending column. On the other hand, if you had 0, 3, 0, 3 as I, J, K and L, that would represent the entire matrix, the whole rectangle. Alright? What did we say? We are going to check. So check if this entire rectangle represented by I, J, K and L has all of its cells set to 1. So that will give you a Boolean value. Boolean of ones. So once if all the cells are set to 1, that will be true. Right. If all of them are set to 1, Then set them to 0 in a new matrix. Matrix is equal to, what's that? Set to zeros the rectangle of I, J, K and L. Cool, so you have the new matrix. Int G is equal to Grundy of the new matrix. Alright, so we have the Grundy of the new matrix. This is a recursive function, it's again going to come back and do all that processing. What do we need to do from this? Well, you know that we need to find the max of all Grundy positions from a given position. So we need a set S, and we need to store this value in this set. So S dot add G. That's what we do. We have added this value to the set, and that's all that's required really. Over here, initially we should look at if position is equal to 0, then return 0. That's the only base condition. So that's the single base condition that we have, and otherwise we go through this entire thing and recursively go on calling Grundy of a given position. Now, as for the dynamic programming part, when you're trying to find out Grundy of a given matrix, you can check if in a global variable, so set S will come here. If this global variable of Grundy array has on its position not equal to -1, so you have some value here in this global variable, then you should return that. Then return Grundy of position. This is just the dynamic programming part. You return the Grundy of the position, and when do you store it? Well, if you had to go through this, then you should store it. So int G is Grundy of this, Grundy of mat is equal to G. That's it. That's all we need to do. Of course, we need to put in some ending brackets, but that's fine. I'll be sharing the code for this in the description below. So, pretty simple approach. Find out all possible rectangles. Check if all of them are set to 1, if all the candles in that are set to 1. If yes, then set them to 0 and get the new matrix. Find out the Grundy position, the Grundy number for that matrix. Store it. Add it to your next set. And finally, I'll just write it over here. Return the max of set S. So all the Grundy numbers for all possible positions have been found out using this rather simple function. It looks a little untidy over here, but in the code it will look simpler. So you can check that over there. So we are nearly done now. We have this range left to right, and what we could do is use the Sprague Grundy Theorem, which states that if you want the result of a given game, that is equal to the XOR of all possible positions, all possible sub-games from this game. So that is equal to XOR of Grundy of left and all the way to Grundy of right. So you have the Grundy numbers for every possible position. So Grundy of left to right, if you want to take the XOR, you could go in a linear fashion, which would take you order n time, which means that you have order qn requirement. Q queries, order n for each, order qn is what you have. Of course, we can speed this up. The first thing that should come to your mind by looking at range queries and point updates is some sort of range data structure, and one of them is segment tree. So in case you don't know what a segment tree is, you can check out the link in the description below. but we'll be using that to solve this problem right now. We have a segment tree, and you see that XOR is a commutative operation, so we can actually store values in the parent using its children. So have a look at this. This is index 0 in our original array, so the first matrix. The first matrix is being represented by 1, 1, 0. All of these numbers are binary so that we can see the XOR happening. So take both children, store that value in the parent by XORing them. So A XOR B is what the parent will have, assuming A and B are children. So let's XOR these up. We have 0, 1, 0. XOR these gives you 0, 1, 0. XOR 0, 0, 1. XOR 0, 1, 1. Let's go to the parent. 0, 0, 0. Wow. What about this? 0, 1, 0. These two give you 0, 1, 0. So the segment tree is now built. In case you have any extra elements in the segment tree because you're making a complete binary tree, the null element here is 0, 0, 0 because that has no effect in the XOR value. X XOR 0 is always equal to X, and that's why that's a null value. Alright. So how are we going to answer queries? Simply really, if you know about the segment trees, then you know that let's pick up something like this. Yeah, this is your range. These are your indexes 0, 1, 2, 3, 4, 5, 6, 7. So from 2 to 4 is the range that you're looking at. What can we do? Well, we start from the top of the segment tree. We see its range is between 0 to 7. So we have to query both its children. Come here, you see that the range is from 0 to 3. Does our range fall in that? Yes. So query both its children. This has a range of 0 to 1. Does our query lie in this range? Does 2 to 4 lie in 0 to 1 at all? Any intersection? No. So this returns you a 0, 0, 0, null element. You come down here and you see that 2 to 4 lies entirely, 2 to 3. 2 to 3 lies entirely within 2 to 4. So this element is responsible for all of its children and returns a value 0, 1, 0, the element here. XOR these two, what do you get? As return value 0, 1, 0. So that's from the left child. Right child, responsibility from 4 to 7, query both its children. Responsibility from 4 to 5, query both children. Is entirely responsible from 4 to 4 for the range, so it returns 0, 1, 1. This is completely out of range, returns the null element 0, 0, 0. 0, 1, 1 is returned from here. From here again completely outside range, so returns 0, 0, 0. What do we have here? So 0, 1, 1 XORs with this and gives you 0, 1, 1. These two elements XOR to give you 0, 0, 1. Let's see if that's correct. Take these three elements. This will have no effect in the XOR. So these two. 0, 1, 0, 0, 1, 1. 1, 0, 0. Ha, thank God. It's correct. So, so the thing is, you can find out the XOR values of any given range using this segment tree. And every parent is going to have the XOR of both of its children in it. Let's just go through a quick update operation in this. So let's clear this up. Alright, so now update. Which one should we choose? Pick this one and let's set it to 1, 1, 1. So let's light all the candles in this thing. Let's make it a little less depressing. 1, 1, 1. What's going to happen? Its parent needs to be updated. So it sends that call to its parent, please update. Parent looks at left and right child, says that okay, XOR of this is 101. Now its parent is again updated. Look at both children. We have 111. Wonderful. So yeah, that's what they're set to. What about its parent? It's set to 101. And so this is how updates will happen in this segment tree. Alright. Query operations we saw were just taking the XOR, and update operations are as explained right now. One thing I missed in the query operation is that when you take the XOR of all Grundy numbers between left to right, of all the matrices between left to right and the Grundys, if it equates to 0, then the player playing right now, the first player, is losing. So lot C will be winning. And if it is not equal to 0, then Pishty is winning. Alright, this is just the theory of Sprague Grundy, you can check it out. But this is how you'll be outputting answers. This is, in fact, the most important thing. You'll be outputting answers this way. XOR of all the Grundy numbers will tell you whether it's 0, in which case lot C is winning, and if not, then Pishty is winning. So Pishty and his birthday is solved. It was a simple problem if you think of it. If you know the theory and the segmentary data structure, it should be quite easy to solve. I'll be sharing the code in the description below. If you have any doubts or suggestions, please leave them in the comments below. I'll be happy to look at them. And until next time, thank you.